Do it quietly. And, oops, sorry. And you will talk about airtightness and internal airflows in multifamily buildings.
Well, first of all, thank you all for making it to the end of these 2 days. And yes, you get to hear from me one last time, but I promise this is the last time you'll hear from me at this particular meeting. Maybe we'll talk to each other again in the future. So the last thing we're going to talk about today is specifically looking at multifamily buildings. And this has become a topic of interest in the US, certainly in recent years, because we focused so much in the past on single family buildings. But it turns out that multifamily testing is probably just as important and maybe more so. And we've also heard a lot today about measuring the exterior envelope of buildings. And what I'm going to talk about today is all this other stuff that happens inside of buildings, whether that's vertical airflows in lifts and the airflows in and out of apartments, but not to the outside. Oi. My Japanese is so poor, I can't read that. I'm sorry. Can you help me? Thank you. And these internal leaks interact with all the things that also create flows through the external envelope, whether that's mechanical systems, whether it's the weather. And so these things they are linked together, but they are subtly different, I think. And when we talk about this, I'm going to use the word compartmentalization, which is a very long English word. Basically, what it means is that we're not just concerned about how much leakage there is in these exterior parts of the building, but also the interior and how much separation we get. And I wanted to show this quick illustration because on the left-hand side there, you see this drawing that I used previously, and you've seen from a few of the presenters about the stack effect in a building, how it's big at the top of the building and the bottom of the building. If we compartmentalize successfully, if we seal every unit in a building, we get the picture on the right-hand side where you can see for that exterior envelope for the individual apartments, the pressures are very small compared to what they are for a long vertical shaft. And that makes a huge difference when we're talking about how much air exchange we get through the exterior envelope. I guess a good question is, where are these leaks? They're not around windows or doors in the exterior of the building, so where are they? Well, it turns out even if we have, the most perfect poured concrete structure in the world, we're going to drill some holes in it because we want to do things like install wires, we need to install plumbing. Sometimes the interior walls are constructed out of things like we have the illustration of here, where it's a pressed piece of sheet metal that's used to hold the walls together. It's full of holes, lots of air can flow through it. So there's plenty of opportunity for leaks, even if we have something like a poured concrete building. As with all of these things, we have to have some metrics, right? And basically, we use very similar metrics for compartmentalization as we do for the exterior envelopes of buildings, where we take some airflows and we tend to normalize by the area. But when we usually talk about compartmentalization, at least in the US context, the area we normalize by is all 6 faces. It's not just the area to the outside of the building. It includes the floors, the ceiling, the walls. And so we have to think a little bit more carefully about when we compare the metrics for compartmentalization to exterior envelope leakage, because we're using a different area to normalize by. In North America, we have some standardized tests, but they're really not measuring what we want. I listed all of these tests here, but these are really all tests designed to measure exterior leakage. And some of them have indeed been adapted to do compartmentalization to include interior partitions and so on. And in fact, I realized that I have made a glaring omission here. There is, in fact, one standard that is specifically for testing individual units that gets used in the US that I forgot to add to the list. I got so focused on just separating out the leakage to outside from the leakage to the rest of the building, totally forgot about it. Anyway, the one test to add to here is a test by an organization called ResNet. And ResNet represents the home energy raters in the US. And they do a lot of testing of buildings. And they developed this test method to specifically test the leakage of apartments. And it has extra requirements for things like you must have at least 2 square meters of open area to the outside when you're testing, so you don't introduce extra pressures. If you put your fan in the doorway, you haven't included the leaks of the door. And so that test method adds in a little bit more leakage to account for that. So it has some things that are really, really specific for apartment testing. And I just want to go through a few examples of how we might possibly do these tests, even though these are not standardized tests. This is what the industry currently looks at. And this first example here is for some houses that are all in a row. And I'm going to raise this principle, which is going to get used all the time, which is we want to neutralize the unit-to-unit pressures. And that lets us isolate the leakage to outside from the total leakage. So often tests are done twice. And this is the first example I'm going to give. At the top there, we're only pressurizing one unit, and we measure the flows through all of the surfaces all at once. Then what we do is we pressurize the neighboring units, so we have no pressure across the walls between the unit we're testing and the other units, and we measure a different flow. And that difference is the flow through the interior surfaces. And this is sort of a standardized practice. It looks kind of easy when I show it like that. Well, it gets a little trickier if you've got a floor plan like this, which might be, what you might more typically think of for multifamily buildings, where you have what we call common entries with corridors and so on. Then you can do, again, 2 tests. On the right-hand side, we see where we only pressurize the one unit, and we measure all the leaks in all the faces of the apartment. Then we can put some fans in maybe the main doorway to the building and pressurize all the rest of the building. So now we've got 0 pressure across those interior partitions. And again, we're just measuring the leakage to outside. We do some subtraction, and we can figure out how leaky we are to the inside. But what if you got buildings with corridors? And we're obviously not going to go through every case here, but you can see it can get kind of complicated when you're trying to pressurize units that are above you, below you, to each side, pressurizing the corridor separately. And having done some of these tests, I can tell you, even with the most careful testing, you can be very, very confounded by things. For example, this ceiling is not really the ceiling that you see. If we pop one of these tiles off, you'd see a big open space. It's full of ducts that connect this space to that space. And those interconnections that you can't see that connect places together, we find surprisingly often, even in residential cases. And so even though you think you've pressurized all the units that your unit is connected to, maybe you haven't, and I've certainly had that experience. So if you try out those test methods, what do the results look like? Here are some example results from a paper by my good friend Dave Bohack and others, where they tested a bunch of buildings. The range here in each of these is the range that they got from testing all the units in one building. So just looking at that, you can see that not every unit is the same, even in the same building. You can sometimes have a big range for some reasons we'll probably get into. The green results there, that's just the leakage to outside. And the blue is the total. So you can see that something like 1/4 to 1/3 of the leakage goes to outside. The rest is all leaks to the corridor, to adjacent units, or what have you. And so there is a substantial amount of the total leakage that is not to outside. And I picked this one study because the figure was nice and clear. There are other studies that have shown some similar results, and we'll have a look at those in a couple of minutes here. One thing I wanted to just sort of pick out of that same data set was how much leakage goes to outside. Because if we're concerned about air exchange for air quality, and we want to do some energy calculations, that's probably the number we're interested in. And you can see there's big variability even for an individual building. And that's because, you know, if you're in the corner, like we are in this room, you have two faces to outside. If you're at the very top of a building, you also have the ceiling. So even within the same building, you can experience these very big differences in what fraction of leakage is to outside, which means when we talk about, you know, sampling and testing, we have to bear that in mind, and we might have to test more units than we think. There's also, of course, the fact that not every unit is physically the same size in an apartment building. Sometimes they are irregular, sometimes not. Somebody has to live in the penthouse that is 5 times the size of all the other units, right? And then finally, construction variability, right? I mean, often when we're doing air leakage tests, we're trying to find out how well did we build? Did we meet a construction standard? Clearly, there's variability from unit to unit. Some studies have looked at, does it depend on how the building is built? And in this study, they split the tested units into 3 categories. Red is concrete structures, poured concrete. The yellow is concrete structures, but they have all concrete partition walls. And the blue is wood frame. And you can see that, as you might expect, if you have a poured concrete structure and all the walls are also poured concrete, you do see that we get much, much less leakage. But there's still a huge amount of variability, right? And if we were statisticians and we looked at this, we might say, well, is there really a difference given this huge unit-to-unit variability? So it's quite difficult to a priori say, oh, if we pick this one construction method, everything will be great, because maybe not. To break this down into a little bit more detail, here we're looking at the fraction of leakage that goes to the interior. And you can see the range here is from something like 10% to something like 100%, not very helpful, right? You've basically captured the full range of what's available. And again, this is, you know, broken out by how the buildings were built. And I think the message here is that you're not guaranteed to have a particular leakage level or a particular split between inside and outside based on your construction approach, right? And also, there's a lot of building to building variability. And I think this implies, and I think I probably said this earlier about total leakage testing, this means we probably do have to test, right? You can't just say, I built using a certain construction technique, and so my building is great. I don't think we're going to be able to say that. We're going to have to test our buildings. We've heard a lot about that in the last few days. Sometimes studies are done where people try to fix some of the leaks. And I just picked one example here where the little piece of the pie that's the dashed red line, that was the leakage reduction they were able to get during this retrofit program, where they only sealed the leaks to outside though. They did not attempt to seal the rest of the leaks. And they did some other tests to try and break down, you know, where are the leaks? Are they going up and down in the building? Are they going side to side? Are they going to the corridor? And you can see they're kind of, you know, there's nothing that's particularly small other than the little green slice of the pie is kind of interesting. And this has been observed in some other studies too, where generally the leakage is not from side to side. It tends to be up and down. It tends to be vertically. And that's because we run a lot of our utilities, the electric wires and the plumbing tends to get run vertically in multifamily buildings. And things like stairwells, they run vertically. And that's what's connecting these units. So there's a lot less leakage side to side than there is up and down, which is kind of interesting. And if I wave my hands and say I looked at lots of studies, I can put some numbers up on the screen. That these are very squishy, obviously, about where do we think the leaks are, right? And I split out the 2 different styles of building because if you don't have a corridor, we have a style of building in the US, I think some other countries have, where you simply walk up and down. There's no corridor that's a sealed off part of the building. We have to pull that out because there's no corridor leakage anymore. That's leakage to outside. But anyway, the point is that there's very little leakage side to side. There's some leakage up and down. If you have a corridor, you tend to leak to it, probably because that's where the door is. And certainly in some HVAC systems, we are deliberately supplying air via the corridor as a supply air system. And so you have a question about, well, the door leaked, but it's supposed to leak. And I don't know how we you know, deal with that from a construction quality point of view. And there's also often parts of an apartment building that are not the dwelling units. They're other things like laundry rooms, or maybe there's a shop in the basement. And so some studies have tried to separate out, you know, if we look at what fraction of the building volume is the common area, as in not dwelling units, versus the fraction of the leakage. And we find that most of the little dots here for these different buildings, they're above that line of equality. So it seems like we might be paying more attention to our tightness for the dwelling units and less so to the non-dwelling part of it. So I've just talked about leakage. That's how big are the holes. The real question is, how much flow do we get? And I think this is a key issue that has come up again and again in conversations I've been having, trying to write standards and so on, is sometimes there is a disconnect there, right? And what we find, probably not surprisingly, is that if you measure the pressure differences across these interior partitions, they're almost always much lower than the pressure differences between inside and outside. So even if we have the same leakage to the inside as to the outside, the flows are very different. They're much, much lower indoors than outdoors for the same leakage. And some people have tried to measure that using tracer gas experiments to actually measure the airflow. Not many studies have done it, I have to say. And I pulled a figure here out of one study where they tried to break it down with, again, this is tracer gas studies about where the air went from the unit. And what we see is that, again, a big range. These are suites all, I think, in the same building, a big range from unit to unit. And also, does it go to outside? Does it go to the other units? It's mostly going to the outside on the corridor, very little to the other units. There's been other studies done where I couldn't find a nice figure. I just pulled a sentence out, right? Typically, we get about 4% of the total airflow that's in and out of the unit is going to the rest of the building rather than to outside. But sometimes it's 40%. So what do we do? Again, I think that comes down to testing, right? In other words, the air tightness still matters because you could get a lot of airflow if you have a leaky building, but it's usually pretty small. And I'm going to wrap up here with a couple of slides that you can all boo if you want, because it's simulations and we didn't measure it. All the previous data was actually measured in buildings. So here we did some simulations using a tool called Contam. And we were looking at, if we release a contaminant in one unit, where does it go? You know, and it's based on those leakage parameters I showed you earlier. Lots of stuff going on here. So CO2, we understand what that is. PM 2.5 is particles, and FRM is short for formaldehyde. The green bars are, what if we release something at the top of the building? So if you're in the top unit and you release something, where does it go? It turns out we don't get much of that in the rest of the building. It leaves. If you are releasing the contaminant from a unit at the bottom, that's the red lines, or somewhere in the middle, those are the blue lines, we get a lot more contaminant transport. Okay. Going from left to right, we also changing the leakage, going from tight to leaky. The current ASHRAE standard is the bar in the middle of those three, just for some sort of a reference. But you can see that these are, as I noted here, this is the worst case. And we looked at the worst case just because we were interested in disambiguating between the different leakage levels and so on. And in the worst case, at the 62.2 leakage level, I gave some results here for about how much transport we're talking about. And in terms of CO2, we're adding about 25 ppm from unit to unit, about 4% of the total. For the PM and the formaldehyde, we get slightly less transport. That's because of some deposition mechanisms happening in the transport here and so on. But it's clear that it matters where you release stuff. But I think generally speaking, transport is relatively low, so long as you're meeting some reasonable standard for airtightness. And there's just very, very few studies that have measured this sort of tight construction transport. A very recent study done in California at UC Davis looked at they had about between 0 and 3%. So 3% was the worst case of CO2 transport from unit to unit. And for PM 2.5, it was so low they couldn't even measure it. It was unmeasurably low. Some of that's because particles love to deposit when they go through little cracks. or particularly if you go through a wall that's full of insulation, because insulation kind of looks like a filter, and it indeed acts like a filter. In the interest of time, I'll skip these funky pictures. We can talk more about them later. I don't want to go into detail. Basically, this is just a heat map of if you release a contaminant in a zone, where does it go? I just want to show that most of the travel is vertical. So when those worst case units are the units above where you are. So if you're cooking, where does the odor go? It goes to your neighbors who are upstairs. Some people have done simulations to look at the energy performance. Now that might change. And going from left to right here, what we're looking at is, what if we seal the exterior enclosure? We get a reduction in energy use. In the middle, we have, what if we just do the interior and not the exterior? And we get close to the same, which is kind of interesting, right? We often focus on the exterior envelope, but doing the interior cuts down a lot of the airflows that are transporting energy around. And lastly, it's best to do both. Ben's looking confused. He'll ask me a question later. And just to wrap up here, there's a certain degree of uncertainty in measuring these airflows, compounded with a lot of degree of uncertainty in what the pressure differences are. Between them, it means we're quite uncertain about those flows. Now, I think from the simulations and measurements, we know the flows are low, but we want to, we'd like to have more certainty. So there's been some development recently of more advanced testing techniques where we do things like introduce a second device so that we can change the pressures over a range and at the same time measure more than one flow at once, which is a key thing. And if you can measure second flow, we had a great discussion earlier today about using, just using the stack effect and opening some new holes in a building. This is kind of doing the same thing. Like you're introducing some new flows, you're introducing some new holes that you've measured the airflow through. And those techniques look like they have some good promise in terms of really getting a much more precise way of measuring all these individual leaks. We have tightness standards, of course. I mentioned the ASHRAE one. It's 100 liters per second per 100 square meters, or I could have said 1 liter a second per square meter. Might have made more sense. Please don't ask me why we use this version. There's also LEED certification in the US for these sort of things. And I just wanted to compare those numbers to what Passive House requires for the exterior envelope. And we're getting sort of down close to those Passive House levels of tightness. And that's the worst you can do, by the way, in the ASHRAE standard. And I'll stop there, and I will just conclude with saying that this is still kind of a new thing. We've sort of got used to the idea of measuring the air leakage of exterior envelopes, translating that into an energy usage, translating it into an air exchange to dilute contaminants. But thinking more about what happens inside multifamily buildings, I think is going to be super important. You can definitely control energy, and you can definitely control the transport of contaminants. And that's interesting. We talked a lot today about the transport of pathogens, for example. And boy, I'm sure several of you in the room got a lot of questions like I did when COVID started about what happens in multifamily buildings. Am I infecting my neighbors? Are my neighbors infecting me? These are important questions, right? But usually we're talking about odor transport. That's the number one complaint, right? But there's a whole gamut of things I think we want to understand better. And I'll stop there. And I think we're very close to the end, but I may have shaved enough time off for a question, Valerie. For the win. Thank you. Do it. And Valerie, if we take a couple of questions, do you have a plan for the discussion afterwards? Never mind. I'll. Anybody got any questions about the interior air leakage of buildings? Ben does, apparently.
Ben does. We have 12 minutes for discussion with every speaker, so you can ask questions to Iain and every speaker.
I'll do 2 questions, then I'll let.
So we can go for 12 minutes, Iain.
We won't, but go on.
I don't think I've ever gone that long. I'm really interested in the finding that by just tightening the internal walls, you get a reduction in energy. Mm-hmm. I would, if I was modeling, my initial assumption might be that the delta T between spaces was 0.
Yeah.
So what's going on?
I think it's mostly this, right? So when you compartmentalize, internally,
I
you
see.
massively reduce the pressures across the building envelope.
Yes.
And if you massively reduce the pressures, you massively reduce the flows. So the total airflows for those buildings changed a lot when they sealed the interior partitions. So I think it's mostly this, Ben, is what we're seeing.
I think that's a really wonderful way of answering a question. Brilliant.
Does that make sense? It's the
Complete
fact that
sense.
compartmentalization.
Total sense. That's absolutely ingenious.
It's not intuitive, but it really does reduce pressure.
It is, I think.
Well, maybe.
I should have got it.
No worries. Is that it? We can go to general questions then, maybe, Valerie?
We can go to any questions.
All right.
Is there another
Do I have
question?
to answer any questions, or can
You
other
do
people?
have to answer a question about the Belgian regulation, please.
Okay, all right.
Okay, Ben, go ahead.
I've got a general question, and it's for Peter.
Peter.
I was really interested in that you have transitioned to 100% blower door tests. I'm just imagining the outcry if this was done in the UK, and they would cite things like cost and hassle and things like that. How did you do it?
As I said, so it was not from the beginning an obligation. So we had a lot of discussions in the past because we took 3 or 4 year discussions to the legislation about a lot of things. But in the beginning, airtightness, there was no worry about because there was no need for testing. And so after a while, I think by experience, the constructors saw that, okay, testing it was much more cost effective because you could go from 12 to 4 instead of putting 5 centimeters more of insulation. So I think you are now 17 years later, so it has become an opportunity. Like there is also no obligation for applying heat recovery, but nobody is installing balanced ventilation without heat recovery. Nobody is installing today mechanical exhaust without demand controlled ventilation. So I think there's a big difference psychologically between you have to do it or you have the option to do it. And I think, yeah, contractors look to their money. Yeah? What is the cheapest way to achieve the goal? What I think is also quite important, that was very important politically when I showed this graph that 4 years level 100 and then 80, it was on purpose that the level 100 was basically what they should have done before. So the idea was change your mind. You have now to report what you have done and you have to do what you report, which was a completely mind change. And so after 4 years, I think also the government followed each year, how is the progress on site? And so when they strengthened the requirement to 80, they could show, okay, but today a substantial part already is at the level of 80. And then they went to 70, 60. So I really believe that not putting the requirement and also not having a maximum limit has been crucial to achieve that. Also, don't underestimate the issue of discussion. I assume that you have a requirement of 5 and you achieve 6. Who has to pay for it? You cannot identify if it is the window installer, is it the roof manufacturer? So here, okay, there is no requirement. And so most of the buildings are done, I would say, by contractors who construct regularly. So after a while, they know more or less, I can count on a level of 3 or 5. And so they take a certain, let's say, level below the requirement. So I think overall that it was crucial to achieve that approach. No obligation. And also, of course, the fine system. The fine system has been crucial. And also that has taken a lot of discussions. In the beginning, the contractor said, you are crazy, you are going to charge us money. But then we said, you want to have correct competition. Yes, we want to have a level playing field. And so the good contractors are protected against those who fraud. And so but it was a heavy fight to get these fines in, because for the building sector to be confronted with fines is. But the consequence was also the government cannot oblige to make the building compliant, because to do that in the Belgian legislation, it has to be done by a judge. And we said we don't want the involvement of a judge because that's a low priority for them. So it should be handled by the administration. But the idea was, okay, but if you buy a house and you see it's not compliant, then as a private person, you are very strongly positioned to claim to your contractor, I must have it compliant. But then it's on the private legal base, not at the level of the government.
Peter, may I ask a follow-on question? I just want to make sure I understood some of the data that you showed, that you have not observed an increase in air tightness over time. Was that correct?
Average airtightness over time, yes.
It has stayed the
Yeah,
same.
yeah.
The reason why I ask is because we've observed the opposite of that in North America, where we found that the more homes got tested, the better builders were at building tighter. Some theories have been that they know they're going to get tested, they do a better job, right? It could be that we started in the US from a much, much leakier place, right? So maybe you already had homes that were not very leaky.
But to be clear, the average airtightness of the building stock has substantially improved between 2006 and 2020. Because in 2006, this 1% were typically passive house builders and these kind of things. So the majority was not paying attention. And so therefore, I think overall, that's why I said from 1 to 100%, that is the gain.
Okay, so only the good houses have ever been tested.
And at the moment, it are all the houses who are tested.
Excellent. Thank you.
So the gain has been very substantial, I think.
Thank you. So I have a question for you. In the page 15 of your presentation, in Belgium, the product like ventilator, our products, need to register the government body or something. Is that right?
Very important. You don't need to register. So that's really voluntary. Even in the European context, you cannot oblige national database because that's against the free trade of goods. But what we agreed with this industry was, these are the procedures. If you put the data there, the architects and so don't have to worry about, is this commercial information correct? So it is not needed. So you can come on the market and say, these are my product data. But there is indeed a risk that architects will say, okay, but can we trust it? But so there is no need at all to do it. In practice, the manufacturers do it, but it's not obliged.
So, because I asked you, we have the test report for ERP Lot 6 adaptation. So our European product have like a certified report for the body in Europe. So I confuse not only European Lot 6 report, but for Belgian special report certification or something, no?
So the procedures are based on European standards. There are no Belgian testing procedures, but we agreed on how should you report it, which laboratory can do it. And so that was all discussed with the European context in mind. So I think the underlying idea is easy access to reliable data. Reliable, so to be in a strong position for the fines, easy to make the lives of the architects and the contractors easy. And it's also to have a level playing field between manufacturers.
My understanding is no need to register more from the manufacturing point of view. But how to say, enough to provide the existing data like Lot 6 data or product to specification sheet and so on. Is that enough?
So if you go on the website, you will see, for example, for heat exchangers, ventilation, there is a test protocol. And normally it's based on European or ISO standards, and it will specify who can do the test. But in principle, all laboratories meeting the requirement can do it. So you have to follow the protocol. But I can imagine that if you have done the test in your own laboratory, that probably not accepted unless you have an accredited laboratory. Yeah.
We have time for very last questions. We come to the conclusion of this workshop. The very last questions? No? So I think Ahmed will start the conclusion and how we will do it.